Hello and welcome to today's webinar, Integrating Carbon Capture and Storage Technology Using Simulation, hosted by Modelon. My name is Swati Tyagi and I'm Modelon's Marketing Manager. I'll be starting things off on today's webinar. For the speakers of this webinar, we have Modelon's Energy and Power Industry Director Stéphane Vallue and postdoctoral researcher at Chalmers University of Technology, Ruben Mocholi-Montañez. Before we get started, let's go through a few webinar housekeeping items. This webinar does feature a live Q&A session with our regional moderator after the webinar. To ask a question, simply locate the Q&A option at the menu below and enter your question for our moderator to see. We will address questions after the presentation. Thank you for attending, and I will now give the floor to Stéphane Vallue.
Thank you, Swati, for the introduction. So my name is Stéphane Vallue. I have background in electrical engineering from Grenoble Institute of Technology in France and a PhD in control from Lund Institute of Technology in Sweden. So the last 15 years I've been working on the development and the application of model-based methods for the energy sector. And now I'm currently working at Modelon as Industry Director for Energy and Process.
Thanks, Swati, for the introduction as well. I'm Ruben Mocholi-Montañez, and I'm postdoctoral researcher at Chalmers University of Technology. I hold a Master of Science in Mechanical Engineering from Lund University in Sweden, and a Master of Science in Industrial Engineering from Polytechnic University of Valencia in Spain, and also a PhD in Energy and Process Engineering from Norwegian University of Science and Technology in Norway. Currently, my main role is to conduct and supervise research and development projects on energy technology with focus on the power and steelmaking industries. And I have more than 5 years experience with dynamic process modeling and simulation using Modelica technology. Even if my current affiliation is Chalmers University of Technology, the work that I will present today was conducted while I was working at Norwegian University of Science and Technology.
So here is today's agenda. So I will start with an introduction to the carbon capture storage technology. I will first explain what this technology actually is, and then I will explain why it should be adopted by the power industry and how it can be efficiently implemented using simulation technology. And then Ruben will be presenting the scalar process and the integration of the capture plant with the power plant. To conclude, we will present some results and takeaways. So obviously there's a need for decarbonization technologies. So CO2 is one of the major drivers for climate change. Since the atmospheric concentration of CO2 has increased by 40% compared to the pre-industrial levels. Consequently, governments worldwide are setting targets and implementing policies to reduce CO2 emissions. So there are basically three options for decarbonization. So the first one is about improving the energy efficiency both on the consumer and on the producer sides. The second option is about increasing the share of renewables in the power industry. So renewables like solar and wind energy systems. And the last one is the one that is in focus in this webinar is about actively capturing CO2 using CCS technology. The goal being to develop a reliable energy system that is compatible with the IPCC's 1.5 degrees scenario. So to achieve this goal, we will be obliged to combine those options. So here are the different steps towards the decarbonization. So the first one is to better understand the conventional technologies to make them more efficient and more flexible. The second step is to develop emerging technologies such as the renewable energy sources, CCS, storage technologies that are large scale and easy to dispatch, and also electrical vehicles. The third step is to integrate those emerging technologies. And here the key enablers for this integration are storage to address the uncertainty and the variability of the intermittent renewable energy sources. The flexibility, so we should have a flexible backup energy systems. We should also have a smart and reliable distribution system. And finally, we could also implement demand-side management strategies. The last step is about analyzing this full integrated system that is distributed and heterogeneous. So at Modelon, we believe that the solution to implement those steps successfully is based on system simulation. And this is really in line with the Internal Energy Agency report from 2014, which identified a framework of systems thinking as a key enabler to successfully integrate all those systems. Today, we will not talk about the full integrated energy system of tomorrow, but we will focus on CCS as emerging technology. We will also talk about its integration in a flexible manner into the existing energy infrastructure, and we will be analyzing the interaction between the capture plant and the power plant. So why have we chosen this technology? This is because it has several advantages. So first, CCS can quickly and drastically reduce CO2 emissions from use of fossil fuels. If it's combined with biomass power plants, then it becomes a negative emission technology, meaning that it's not only neutral as most of the renewable technologies, but it's actually removing CO2 from the atmosphere. Then the CCS chain has been technically proven at commercial scale in coal-fired power plants for years. And it's a major technology that is ready to be deployed. It's a cost-effective way to reach the IPCC goals of 1.5 degrees. It has been also discussed in the IPCC report from 2014, which showed that the pathways that are not including CCS are about 130% more expensive than the pathways with CCS. Finally, the CCS technology is easy to dispatch and integrate, especially if it's a post-combustion CO2 capture technology, the one we'll be talking today, because it's an end-of-pipe technology. So what is actually CCS, carbon capture and storage? So it can be defined as a family of methods for capturing and permanently isolating CO2 that otherwise would be emitted to the atmosphere and could contribute to global climate change. So it's normally implemented in 3 steps. So the first one deals with the capture of CO2 locally at the thermal power plant or at the industrial process plant, which otherwise would have emitted CO2. So we typically capture CO2 from the flue gas. Then we compress this CO2 to a high pressure liquid that can be transported by ship or pipeline to a remote storage location, typically underground in a geological formation or in the ocean. So how does it work? So if we focus on the first step that deals with the capture. So here you see at the top right a picture of a running plant that has been in operation since the late 70s. in Texas in the US. And below you find a sketch of the plant. So it consists typically of two columns. One is the absorber and the second one is the desorber. So in the absorber column, the flue gas enters at the bottom into this absorber column, and it meets solvent that will chemically capture bound CO2 on its way down. And at the top of the absorber, you get then clean flue gas that that is almost CO2 free. The CO2-rich solvent at the bottom of the absorber needs to be regenerated. This is done in the desorber, which operates at a higher temperature through some steam supply system in the reboiler, and steam is typically provided from the power plant. At the top of the desorber, you will collect the CO2 in gaseous form, and at the bottom you will get you will have a regenerated solvent that can be used again for carbon capture. The overall capture rate of such a plant is about 90%, and you also get clean flue gas, almost clean flue gas, and a nearly pure CO2 flow that can be compressed and stored. So this sounds simple, at least in principle. When it gets to implementation, it's a bit more difficult. So there's no off-the-shelf solution to implement this technology, and that's why simulation can be of great help for the implementation. So here's a typical table that summarizes the requirements from a power plant owner perspective. So the power plant owner wants to get a CCS capture plant that has been optimally designed for his specific power plant. That would be time-consuming to design and costly if you don't use simulations. So with simulation, you can run quick and accurate analysis throughout the process development, from early design to commissioning, and in a reproducible way. The second requirement is to minimize the economical burden of the CCS capture plant. So as I said before, the capture plant consumes steam to extra CO2 from the solvent, but it also consumes power to compress the capture CO2 before transport. So we would like to minimize this energy consumption. And that's difficult to do, and that's difficult to get insight into these complex and highly interactive plants. With simulation, you can actually estimate the operational cost, you can estimate the investment cost, and also find the most economical configuration for your particular power plant. The last requirement is about maintaining the plant's performance during load changes, during transients. So it's about keeping the removal efficiency at a constant rate, and it's also about keeping the energy efficiency of the power plant, so the electricity production stable during transients. This is in practice impossible to predict this impact of the dynamics on the plant performance. With simulation, so with access to dynamic models of the plants, you can run transient simulations, you can do control design, you can do process design, and you can also develop strategies to maintain a stable and efficient operation of your power plant and a stable CO2 removal efficiency of the capture plant. And this is this last item, last requirement that has been identified by several people as critical for the future deployment of the CCS technology. So it should be operated in a flexible manner to achieve good load following capabilities. That's what at Modelon we've been working on by developing model libraries to describe the dynamics of both the thermal power plant and the capture plant. So we've developed the last 15 years a library called the Thermal Power Library. It was done in tight collaboration with the power industry and can be seen as a comprehensive framework for simulation optimization of thermal power systems, like coal-fired or gas-fired power plants, or biomass-fired power plants, and other thermal types of power plants like nuclear or solar power plants. So to the right, you see a sketch of 500 megawatt coal-fired power plant from Germany that has been modeled with the thermal power library. So you can see that we can describe almost the entire plant. So from the air system, the fuel system, the boiler, the Rankine cycle. And this was done to study, to assess first flexibility of the plant and to optimize it. Typically during low cycling, so when you ramp up and down the power plant, or during startup. And when you optimize the plant performance, you want to still maintain overall plant stability. So you want to maintain temperature and pressures within reasonable ranges. And you want also to minimize the lifetime consumption of critical components in the steam cycle that are exposed to high thermal and mechanical stress during those transients. At the bottom, you see some figures that show experimental results and simulation results using this power plant model. The one to the left shows an open loop experiment when we increase the fuel flow in a step manner. So you see here that the time response of the power plant is rather big. So it's in the range of 30 minutes. And to the right, you see that the result of an improvement of the control strategies for primary frequency control that makes it possible to increase in 1 minute the power of the power plant for 15 minutes, and that several times in a row. And you also see a good agreement between the simulation results and the experimental data. But we also developed another library in add-on to the thermal power library called the separation process library to describe the post-combustion capture plant. So with this library, you can typically describe the entire capture plant. So here you see a sketch of the model, a Modelon model, with the components I described before, the absorber, the desorber, the reboiler, and heat exchanger. So those models have been validated using experimental data, both in steady state operation and during transients, as it is shown to the right. So we can see we capture well both the removal efficiency at steady state and during transients. Now I will leave the word to Ruben. We'll explain how he applied those tools, simulation tools, on a real industrial case.
Thank you, Stefan. So as Stefan was introducing, we from Norwegian University of Science and Technology decided to explore carbon capture and storage technology using Modelon's thermal power library to model a natural gas combined cycle power plant integrated with post-combustion CO2 capture based on chemical absorption. As has been introduced by Stefan, we need high efficiency, flexible thermal power plants with low emissions. And on the one hand, you have the power plant and also the capture process, and both processes are integrated. Basically, you need heat from the power plant to run the capture process. And we were especially interested on the dynamic aspects, on the transient response of the integrated system, on load following scenarios, on changes on the power plant load. And the key aspect is the fact that the chemical process is considerably slower or much slower than the power plant. So we started by analyzing the performance of the capture process, and for that we developed a dynamic process model of a pilot capture plant. The reference capture plant was the amine plant at Technology Center Mongstad in Norway, which is the world's largest center for testing and improving CO2 capture technologies. The amine plant has a CO2 capture capacity of 80 tons of CO2 per day when it runs with natural gas coming from a combined cycle power plant. And it's a very flexible amine plant that can deal with different concentrations of CO2, typical of natural gas, but also treats gas coming from the catalytic cracker of a refinery. In this case, we selected aqueous MEA as the benchmark solvent. This is the solvent that we used in our study, which is the most widely used solvent. And the flue gas treated was a slipstream of flue gas coming from the combined cycle power plant. In order to build our dynamic process models, we used the separation process library from Modelon. And we used several components representing the main equipment that we can find in this pilot plant. For example, the absorber column, the stripper column, some pumps, heat exchangers and condensers, and the controls. In order to develop these models, for example, if we focus on the absorber, you need to add a lot of parameterization in your model, such as, for example, geometry and sizing of the equipment, process conditions, and so on, and also boundary conditions. And you also need to initialize the dynamic process models. And then by combining the different components, you build the entire dynamic process model. It is, in general, it's a time-consuming task or a challenging task, but once you know how to do it and you know how to develop these models, you end up with a very powerful tool. The dynamic process models are based on systems of differential algebraic equations that represents the key physical phenomena in different components or equipment of the plant. And for example, if we focus on the absorber unpacking segments, the models are based on two-film theory approach for heat and mass transfer, also chemical equilibrium for reactions, rate models for mass transfer, and using enhancement factor modeling approach. So they are complex models representing complex physical phenomena. In order to validate the capture plant model, we generated several cases or several sets of steady-state operation data representing a wide range of steady-state operating conditions. And we compared our the outputs from our dynamic process model with the experimental data for several process variables. Here on the top left figure, you have the lean CO2 loading, which represents how much CO2 you have in your solvent at different locations of the plant, in this case at the inlet of the absorber column. And on the top right, we have the CO2 produced. These figures represent or are parity plots in which you can compare output from the model and the output from the experiments, and we see that there are some deviations between model predictions and experimental results, but those are kept within reasonable bounds for the purpose of dynamic process modeling. Basically, the main conclusion from this validation is that the model properly predicts the steady-state variability of main process variables for a wide range of operating conditions, including as well temperature profiles in absorber column, and a stripper column. We also conducted the transient tests in order to generate transient data for dynamic process model validation from the Technology Center Mongstad amine plant. The tests consisted of applying disturbances to the process by changing flue gas flow rate, solvent flow rate, and reboiler duty in different tests. And by that, we generated different transient data, such as the CO2 desorbed, as you can see in the middle figure, transient response, or the CO2 absorbed in the bottom figure. And comparing in black pilot experimental data with the outputs from the model, which you can see in red, we can see that there is a very good agreement in terms of dead times and lag times between both experimental and model results. By this, we can conclude that the model can be applied for model-based control structure design, and this validation work also proved the capacities of dynamic process modeling applied to large-scale experimental data and gave us confidence towards using dynamic process models for scaled-up applications. We wanted to conduct, with this dynamic process model, one study on analyzing the process dynamics at different power plant loads. And the main reason for this is that it is expected that power plants will be operated in the future more often at par load. It means during a more significant amount of hours of their lifetime. Therefore, operation at par load becomes more important. We did this by applying disturbances to the process at different loads of the capture process. For example, by applying steps in the magnitude of solvent flow rate or the boiler duty. And we basically observed that when you move into, or when the plant is operated at par load, it becomes slower. It takes longer to stabilize the process when it's operated at par load. We also used this dynamic process model to prepare experimental tests, since we wanted to conduct tests at the real pilot plant and analyze the performance of different control structures. What we did is to use this dynamic process model to prepare the test matrix. And we found that having a model that for preparation of the tests is very useful, for example, because it allows you to achieve faster stabilization of the plant during parametric testing, and this saves money and time. It also allows you to conduct pre-tuning of controllers of the supervisory control layer, which it is very helpful. And also, it allows you to better communicate with plant operators and engineers before the testing phase and during the testing phase. Then we moved into the process of scaling up the capture plant and integrating it with the power plant. The method followed consists of 3 steps. First, we selected a process configuration, and we decided to study a combined cycle power plant consisting of a 1 gas turbine, 1 heat recovery steam generator, and 1 steam turbine. And the heat recovery steam generator consisted of a 3 pressure reheat configuration, which represents state-of-the-art technology in combined cycle power plants. And then we conducted the scale-up of the capture process so that it can deal with the amount of flue gas that is generated in the gas turbine, and it can capture 90% of that CO2. And we ended up with a configuration of 2 absorber columns in parallel with 1 stripper column or desorber. Then, once we had the integration, we have to design the integration of this process. So we considered a steam extraction from the steam turbine and the low pressure superheater in order to fit or to produce enough steam for the reboiler of the capture process. And this is the main integration boundary. The next step, second step, was to develop dynamic process models of both the power plant and the capture unit. And for that, we use thermal power library from Modelon. For the power plant, we used the several components from the library to represent the actual equipment in the power plant design. So for example, high pressure superheaters, reheaters, intermediate pressure superheaters, evaporators, and economizers, also drums, a steam turbine expansion components, and condenser. And of course also pumps, valves, and the controllers and control blocks representing the control structure of the power plant. And then we also used separation process library from Modelon to develop the model of the scale-up capture plant. And then we managed to simulate in the third step to conduct simulations of the integrated system, power plant, and capture unit in the same tool using Modelica technology. We used this dynamic process model of the entire capture plant and power plant to evaluate the transient performance of the integrated system under power plant load changes. And we also did a study on what we call variable ramping. It means understanding how faster ramp rates in the power plant would affect the performance of the integrated process. And this is important because power plant owners are looking for faster ramp rates for being competitive in the future. And also we used this dynamic process model to evaluate the effects of different decentralized control structures applied on the capture unit on the operation of the integrated power plant. And I will talk now about the last bullet point on control structures. So in order to evaluate different control structures, we selected several promising control structures for this process. As you can see in the figure, this represents the capture plant. And in a chemical process such as this one, normally you have two main control structures for operation. The first one, or the bottom one, is the regulatory control layer, basically, that takes care of stabilizing the process to keep some process variables within reasonable bounds, and also to make sure that the process is stable when changing conditions or process conditions. That control layer normally implies to control levels, pressures, and some temperatures and flows within the entire system. And then on top of that, we have the supervisory control layer, which takes care of those control variables that are of importance for the optimal or economic performance of the plant. And this is the control structure that we want to study, the supervisory control structure. In order to select your control structure, you have to first analyze your degrees of freedom, or what you can manipulate in the plant. In this case, the main degrees of freedom, or things that you can change in the plant, are the solvent flow rate. It means how much solvent you are sending to the absorber and circulating through the system. And the steam flow rate, it means how much steam you're extracting from the steam turbine and sending to the reboiler. And then you have also several control variables that you want to keep constant at different loads. Normally, those are the CO2 capture rate. It represents how much CO2 is being absorbed in the absorber. And you want to normally have around 90% of the CO2 captured. And then it's also important to keep the stripper temperature profile more or less constant. And for that, you normally want to control the stripper bottom temperature. And then you could also select some other control variables, such as, for example, keeping liquid-to-gas ratio in the absorber column constant. By combining several manipulated variables and controlled variables, you could generate different control structures. So for example, control structure A will imply to use the solvent flow rate to control the capture rate and the steam flow rate to control the stripper bottom temperature. Here we show several results for two main cases. On the left, we have as gas turbine load decrease. It means that we are reducing the load of the entire power plant by reducing the load of the gas turbine first. And see on the top left figure, we observe the steam turbine power output. And on the bottom left figure, we have the CO2 capture rate. And as you can see, you have several trajectories in different colors, which represent the trajectories for the same load change when you have different control structures implemented in your capture plant. On the right, we have a similar scenario, but in this case, the gas turbine load is increased, and consequently, the steam turbine power output also increases in the combined cycle, and you also observe a transient in the capture rate. So, for example, if we focus on the control structure A, in which CO2 capture rate is controlled by changing the solvent flow rate, what we observe is that in this control structure, the stabilization of the capture process is reached faster within the hour. You can see that other control structures might be taking longer to stabilize, and that means that they might be you are maybe operating the process under non-efficient conditions or less efficient conditions during a longer amount of time. So some conclusions from these dynamic simulation studies. So first of all, we managed to develop detailed dynamic process models of both the power plant and the capture unit and simulate the real-life performance of the power plants during load changes. One of the main or first conclusions is that the CO2 absorption process does not affect significantly the load change following capability in terms of power output from the power plant, but there might be some small amplitude dynamic interactions in terms of steam extraction from the low pressure steam turbine. And that means that that extraction might be oscillating for around 1 to 2 hours. But we also observed that when controlling the CO2 capture rate, the power plant performs more efficiently at steady state of design conditions, and it also requires longer time for stabilization of the capture unit main process variables. However, when we used liquid-to-gas ratio control, we found that the entire facility reached faster stabilization. It means combination of the power output and also the CO2 product flow rate. And as a main conclusion, it is concluded that adding the capture unit to the combined cycle power plant does not significantly affect the practical load following capability of the integrated system. So what we discovered as main benefits of simulation. First, simulation with thermal power library allows you to develop deeper understanding of the process dynamics. And as well, at a pilot plant, it allowed us to, or it became easier to plan test campaigns and also help to communicate with operators and engineers during testing phase. Also, we managed to demonstrate the operation of a commercial power plant with carbon capture and storage using dynamic process simulation. In addition, model-based system simulation proved to be a key enabler for control structure design and implementation. And also model-based solutions with Modelica can contribute to develop the learning curve for flexible and efficient operation of thermal power plants with CCS.
Thank you, Stefan and Ruben, for this presentation, and thank you all for attending today's webinar. We hope you found the information presented today to be insightful to your business operations. Now, before we move on to live Q&A, recording will be emailed to all attendees. If there are any additional questions you would like to address offline, please contact Stefan and Ruben via the contact information shown. For more information about Modelon and Modelon's thermal power library, visit www.modelon.com. And now I will pass it on to our live Q&A moderator.